All right, let's go ahead and look at this first problem here, which is true or false. Is this integral equal to this function? I should really say, is this antiderivative equal to this function? But I'll point out that when we talk about antiderivatives and or integrals, we kind of use those words interchangeably. What I should really say here is this indefinite integral equal to this function here. But I'm going to say antiderivative or just integral because that's pretty typical. So I'm not going to actually do this integral because one, I don't know how to yet. We don't have the technique to do this antiderivative. So instead, the way you should typically check to see if the antiderivative of something is equal to something else is by taking the derivative of the something else and seeing if it's equal to the function you were trying to antidifferentiate. So we're really going to check this by checking to see what the derivative of x squared times sine of x plus c is equal to. So I have to use the product rule. So it's going to be 2x multiplied by sine of x plus x squared times the derivative of sine of x, which is cosine of x, plus 0. And I'll point out that it is certainly not equal to 2x times cosine of x. So this first statement is false. The antiderivative of that is not equal to that because the derivative of that is not equal to that. So I want to emphasize something here that is almost always true. We cannot find the antiderivative of a product by just taking the antiderivative of each piece and multiplying it together. It is certainly true the antiderivative of 2x is x squared. The antiderivative of cosine of x is sine of x. But the antiderivative of 2x times cosine of x is not equal to x squared times sine of x. Later on, when we learn about integration by parts, we will learn how to do an integral like this. It's probably sometime next week, I imagine. On the other hand, unless I made a mistake, I believe the second one is true. Let's check. We're going to find the derivative of negative x squared times cosine of x plus 2x times sine of x plus 2 times cosine of x. We don't really need to write the plus c, but we will. So for each of these first two pieces, we're going to have to use the product rule. So it's going to be the derivative of x squared, which is negative 2x, times cosine left alone, plus, now we leave the negative x squared alone, and the derivative of cosine of x is negative sine of x. Moving over here, the derivative of 2x is 2, leave sine of x alone, plus, now leave the 2x alone, the derivative of sine of x is cosine of x. Finally, over here, the derivative of 2 times cosine of x is just 2 times negative sine of x plus 0. Simplifying or seeing which things add up to 0, I've got a positive 2 times sine of x and a negative 2 times sine of x. I've got a positive 2x times cosine of x and a negative 2x times cosine of x. So I'm left with negative x squared times negative sine, which is just x squared times sine of x, which is indeed the function we were antidifferentiating in the first place. So that checks out. This statement is true. Complicated, right? It's not as maybe as simple as you might have imagined it was going to be. I'll point out that this kind of question was inspired by problem number, I think 36, or number 36 from section 5.3, which is asking you to check if something was equal to something else. And the way you're supposed to check that isn't by actually doing the antiderivative, but by finding the derivative of the thing it's supposed to be equal to and seeing what works. Let's see. So many things to say. Do more of that. Yeah. We've been talking about definite integrals a bit. Let's look at a couple more definite integrals for a moment here before we move along. Do some word problems. So let's say we wanted to find the following definite integral. The integral from 1 to 9 of x squared minus 1 divided by the square root of x. I'll point out that unlike the problem I mentioned in class the other day, this one's totally fine, right? We don't have any place where this function's undefined, so it's totally good to go forward. And this is something that's going to be true a lot. It's often a good idea, or in our best interest, to simplify the integrand, the thing we're integrating, before trying to actually find its antiderivative. So here, it makes a lot of sense to rewrite this as the integral from 1 to 9 of x squared divided by x to the 1/2, or the square root of x, plus 1 divided by x to the 1/2. And then we're going to simplify each of those fractions as, well, x squared divided by x to the 1/2, we subtract those powers and we get x to the 3/2. I missed it. That's what happened to it. It's a minus. Can't you tell it's a minus sign? And 1 divided by x to the 1/2 is going to be minus x to the negative 1/2. And now that we've written everything as powers of x, we're in a good place to just find the antiderivative. So we're going to add 1 to each power. So we're going to get x to the 3/2 plus 1 divided by 3/2 plus 1 minus x to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus c. Definitely you can and should skip this step, because 3/2 plus 1 is something you can do. It's 3/2 plus 2/2, which is 5/2. So we're going to get x to the 5/2, and then instead of dividing by 5/2, we should multiply by the reciprocal, which is 2/5. That's a pretty typical step we skip, is jumping just from this to that. Oh yeah, 3/2 plus 1 is 5/2. Oh, and you know what I did forget though? I forgot my limits of integration here. So I shouldn't be writing a plus c here. I should really be writing a from 1 to 9 there. Sorry about that. Go away. Sound like you never existed. Minus negative 1/2 plus 1 is positive 1/2. And dividing by 1/2 is the same as multiplying by 2. From 1 to 9. Now we're going to plug in. So we're going to get 2/5 times 9 to the 5/2 minus 2 times 9 to the 1/2 minus, okay, when you plug in 1 to any power is going to be 1 every single time. So I really, really don't want to or need to write 1 to the 5/2 and 1 to the 1/2. I should just write 2/5 times 1 is still 2/5 minus 2 to make my life a little less terrible. And here you should go the extra mile and simplify it further, because 9 to the 1/2 power is something we know how to calculate. It's the square root of 9, which is 3. So this ends up being 2/5 times 9 to the 5/2 is 3 to the 5th. 2 times 9 to the 1/2 is 2 times 3. And then you have minus 2/5 plus 2. I don't really want to go any further here, so I'll leave it there. Which feels impossible to stop there, but we could go further. We just don't need to. Maybe. Okay, fine. So anyway, 3 to the 5th is 243 times 2 is 486 divided by 5. Minus 6 plus 2 is minus 4, minus 2/5. So we end up getting 484/5 minus 20/5, which simplifies as 464/5. But we really, like, if this was on the test, you shouldn't do all this work unless you've done everything else on the exam you can. You should stop like here. And then if you have time, yeah, go simplify the stuff if it seems reasonable to simplify it. But if you don't have time, you're gonna get the least amount of points from doing this last bit of work here. The first few steps here were what was important. The last few steps, not so much. Let's look at one more example of this. With this idea of simplifying before anti-differentiating. We have the integral from 0, it's time to make noise outside. This is from 0 to 2 of x times 1 minus x squared dx. I will point out later on, we'll have an example similar to this, except it'll be 1 minus x to the 200th power. And then multiplying out the 1 minus x to the 200th power will not really be an option, although technically it's doable. It takes a long time. We'll learn a different method how to deal with that. So this is going to be the integral from 0 to 2 of x times 1 minus 2x plus x squared, just multiplying out the 1 minus x times 1 minus x. And then we're going to distribute the x to each term and get the integral from 0 to 2 of x minus 2x squared plus x cubed. And now we're ready to anti-differentiate, because again, we've written everything. People often refer to this as writing everything as like powers of x. If you can just write x to a power plus x to a power minus x to a power, then you can usually easily anti-differentiate that. Here we're going to have, let's see, x to the first is going to be x to the second divided by 2. The antiderivative of 2x squared is 2x cubed divided by 3. Welcome, have a seat. And the antiderivative of x cubed is x to the fourth divided by 4, evaluated from 0 to 2. Plug in our limits of integration, so we get, now here's where I would probably start simplifying right away. So I'm going to plug in 2. I don't really need to write 2 squared divided by 2. I'll write 4 divided by 2 minus, let's see, 2 times 8 is 16 divided by 3 plus 2 to the fourth is 16 divided by 4 minus, okay, here's a habit I don't want you to get into. I'm not going to write everything down here, but you should at least think about what's happening when you plug in 0. A lot of the time when you plug in 0, yes, everything's going to be 0, but not always. 2 examples that stick out in my head is, what is e to the 0 equal to? What's cosine of 0 equal to? Right, so be careful. Not always when you plug in 0 do you get 0. So make sure you're checking when you have a 0 there that it's not just 0. Yeah, it's 0. No, it's not always 0. Sometimes it's something else. So here it does end up being 0. 0 minus 0 plus 0 is 0. But definitely check. So then this simplifies to 2 minus 16 thirds plus 4. So I've got 6 minus 16 thirds, which is really 18 thirds minus 16 thirds, which is 2 thirds. Cool. Look at a couple other problems here that I had on my radar. Oh, yeah. So you have to, we talked about the fundamental theorem of calculus last time, right? Like parts 1 and 2. Yes, okay. So I've been talking about it a lot with all kinds of people, so I have to remember if I've talked about it with you all or not. So I should just point out a couple things here. Something that I want you to be aware of. So when we write something like this, I'll just make up something. The integral from 1 to 3 of x squared plus cosine of x dx. This is an example, is a definite integral. And it represents the net area below the curve f of x equal to x squared plus cosine of x that is above the x-axis on the interval from 1 to 3. So basically, area above the x-axis is counted as positive, area below the x-axis is counted as negative. But the point here is really that this represents a numerical value, right? You find, like just in our last 2 examples, right? We did these 2 definite integrals and we got some terrible number at the end. It is a number. On the other hand, this thing here, the integral of x squared plus cosine x dx, is an indefinite integral. Also known as an antiderivative. It represents the antiderivative. It is a function. So I just want to make sure that's super duper extra clear in all of your minds. Definite integrals, we calculate them, you plug in your endpoints, you get some numerical value out, and maybe it's a terrible numerical value. Indefinite integrals, aka antiderivatives, you just antidifferentiate and your result is whatever that function is. That's the main difference between the two. But both of them typically still use the antiderivative to find what you're getting at. Here you just would find the antiderivative. Here you would find the antiderivative and then plug in the inputs. Now that's not always true. There are some functions that don't have antiderivatives at all, or don't have nice antiderivatives that we'd rather not deal with. For example, if I was to ask what's the integral from -2 to, sure, 6 of the absolute value of 2x minus 3, I don't really want to anti-differentiate that because it requires using a piecewise function. I would much rather just draw the thing. So let's draw that function. So the absolute value of 2x minus 3, let's see, it's kind of V-shaped. I know that the bottom of the V is when the inside stuff of the absolute value is equal to 0. So if I set 2x minus 3 equal to 0, I'm going to get x equal to 3/2. So over here at 3/2, that's where my absolute value is at the bottom. And then I'm going to do something like this. I didn't draw that very symmetrically, sorry. And if I plug in -2, let's see, if I plug in -2, I get -4 minus 3, which is -7, and the absolute value of -7 is +7. And if I plug in +6, 2 times 6 is 12, 12 minus 3 is 9. So if I plug in 6, I get a value of 9. And look at my shapes here. I essentially have two triangles, and I can find the area of a triangle. So this integral, which is again the area under the curve that's above the x-axis, is going to be, well, the area of this triangle, which is going to be 1/2 the base, which is 2 plus 3/2, or 7/2, times the height, which is 7. Plus this area here, which is again 1/2 times the base, which is 6 minus 3/2, which is 12/2 minus 3/2, which is 9/2, times the height, which we said was 9, even though I forgot to label it. And look, we found the area. We found the integral. We found the definite integral. And yeah, we could simplify this. It's going to be what, 49 over 4 plus 81 over 4, which is 100 and something over 4, 130 over 4. Yeah, 130, which reduces to 65 over 2. So I'll point out sometimes with definite integrals, it makes a lot more sense to think about the geometry of the shape. Another example that I think we talked about already was if your region looks like a circle. So like, for example, if someone said, what's the integral from 0 to 5 of 2 plus the square root of 25 minus x squared dx? The 2 is kind of throwing me off. Someone used one of the rules of integration that we use kind of all the time that we almost never talk about, which is you can break it up, kind of like with a derivative. If you have the derivative of something plus something, it's equal to the derivative of the first thing plus the derivative of the second thing. We use that all the time without talking about it. The same idea is true here. The integral from 0 to 5 of 2 plus the square root of 25 minus x squared, you can think of and write as the integral from 0 to 5 of 2 plus the integral from 0 to 5 of the square root of 25 minus x squared. There's a rule for this too. I don't really like memorizing it because I don't think you need to. But if I just draw each of these pictures, let's see what we've got. So here's y equal to 2 from 0 to 5. I know that shape. It's a rectangle. And the area of that rectangle is pretty easy to find. Base times height, which is 5 times 2. More generally, actually, yeah, I'll wait a minute to say this, but so this part's going to be 5 times 2, or as I would say, the length of the interval times the height of the rectangle, or the constant value of that function, plus that shape there is a portion of a circle of radius 5. But it's only the upper quarter of that circle, because we're only going from 0 to 5, and this function here, y equal to the square root of 25 minus x squared, is only the top half of the circle, or I should say it's the semicircle. So the area of that region is going to be the quarter of a circle of radius 5. That's going to be 1/4 times pi times the radius squared. And I would probably simplify it because I can't help myself. That's going to be 10 plus 25 pi over 4. Something, yes. So a couple rules of integration you should be aware, I should say rules / properties that you probably should be aware of that I saw him mentioning in class, I think yesterday. Which again, I don't think you really need to memorize so much as just be aware of that they are rules in the first place, are the following. So we have these things. The integral from a to b of f of x plus g of x. You can break that up as the integral from a to b of f of x plus the integral from a to b of g of x. And really most of these things are true whether they're definite or indefinite. Some of them depend on them being definite, like they don't make sense to talk about without the limits of integration. And this is true whether you're adding the functions together or subtracting the functions. And this is a rule we've seen be true for lots of things. It's true for derivatives. It's true for limits. Those are kind of the two examples I have. Right? But basically, if you do a thing to a sum or a difference, you can do the thing to each piece of the sum or difference and then add or subtract the results together, and nothing is different. What else do we have here? We have, yes, the rule I already talked about, that the integral from a to b of a constant is just that constant multiplied by the length of your interval. It's just a rectangle whose base is b minus a and whose height is k. Somewhat more interestingly, a rule we're going to use a lot, if you have the integral of a constant times a function, as long as that constant is multiplied by the entire function, we can always, and we almost always do, like to pull it out in front of the integral. And it almost doesn't even make a difference, really. Like whether you leave it in or pull it out, it's kind of like, yeah, it's there either way. Just like how when you take the derivative of a function that's multiplied by a constant, that constant just hangs out. And then, yeah, let's talk about these last two rules. This last one rule, two rules, sure. So I always think this one's kind of interesting. I'll draw some pictures here in a second. So the general rule here is that the integral from a to b of f of x can be written as the integral from a to c of f of x plus the integral from b to c of f of x. Sorry, from c to b. Ugh, terrible, James. Graphically, here's how this looks. So typically what we're saying here is, well, the integral from a to b of f of x is all this area under the curve here. What we're saying really is that you can break it up anywhere. So if I pick some point C, say, yeah, the area under the curve from a to b is the same as the area under the curve from a to c plus the area under the curve from c to b. Doesn't seem terribly surprising, right? What I think is a little surprising is that c doesn't have to be between a and b. It seems like it should be, but it actually doesn't have to be. Kind of cool. Here's how it works. Let's say here's A and here's B, but now C is over here. So is this statement up here still true? Is the area from A to B the same as the area from A to C plus the area from C to B? Oh, but the area C to B is kind of out of order. So here's what I'm going to write instead. Check this out. Sure. So what I would write here, just kind of start it off, is the integral from A to B, let's call this f of x again, of f of x, plus the integral from B to C of f of x, I'm forgetting my dx's here, that's kind of a crime, is equal to the integral from A to C. And now I'm going to try and make this look like that. So I'm going to isolate this. I'm going to bring that over to the other side. So now I have the integral from a to b of f of x equal to the integral from a to c minus the integral from b to c. And I'll remind you of something we did last time. If you change the order of the limits of integration, it changes the sign of the integral. So this is the same as saying the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx minus minus, so plus the integral from, so it's limits of integration, c to b. Oh, look, it's exactly the same as the thing we wrote up here. Exactly, right? Not even a little bit different, exactly the same. So I think it's kind of cool that what we're really saying here is you have an integral and trying to find the area from a to b under the curve. You can actually break that integral up anywhere you want. And I should stop there. Actually, I should say more. Anywhere you want, as long as the function is defined along that whole interval. So it doesn't actually have to be a place that's between the 2 points, which I think is kind of cool. And there definitely are instances where we will need to break up integrals into multiple integrals because there's an inconvenient point or other things we haven't gotten to yet. Yeah.
Switch the signs. You also need to switch
limits of integration, the order of the limits of integration. So yeah, I should write down that rule as well because I know we talked about last time, but I'm gonna go back and write it up here. So it is also true that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. And I suppose another thing that I don't really think we need to say, but I'm gonna say it anyway. The integral from a to a of f of x should be equal to what? Right. I feel like there's one other thing that, oh, I know, that's true. There's two other rules I want to mention before we do some other stuff. One of them I think is very useful. The other one, kind of. I guess three rules, actually. So here's the one I think is useful. The integral from negative a to a of f of x is equal to 0 if f of x is an odd function. So for example, two examples here. The integral from negative 2 to 2 of x cubed. That's probably my favorite example. It's easy to see. If you graph, actually it's not my favorite example because I'm bad at graphing x cubed. If you graph x cubed, if one could graph x cubed, it would look kind of like that. And if you start at negative 2 and end at positive 2, you can hopefully see, bearing in mind my graph is not perfect, that this positive area over here is exactly the same amount as this negative area over here. And so when you add them together, it adds up to 0 because area above the x-axis is counted as positive, area below the x-axis is counted as negative. Or you could not do that at all. You could actually just do the work. If we did the work, see what happens. If we actually find the antiderivative, evaluate it from negative 2 to 2. I will point out, this is a small pet peeve, but it is a pet peeve. When you say this, you should say from the bottom to the top. So when you're doing this integral, it's x to the 4th over 4 from negative 2 to 2. It is incorrect to say it a different way. Not that any of you said that, I just want to stop you before you even have the chance of saying it from the top to the bottom, because that is not correct. But if I plug in my points here, I get 2 to the 4th divided by 4 minus negative 2 to the 4th divided by 4. And hey, look, that's 16 over 4 minus 16 over 4, which is definitely 0. So if you have an integral from a negative number to a positive number of an odd function, that's going to equal 0. Let me show you one more example, and then let me show you what we use it for. Another common example is like the integral from negative pi over 2 to pi over 2 of sine of x. Sine of x is famously an odd function. Probably draw it pretty well. So I didn't make the very even. Oh well, just like kind of looks like this. And if we're going from negative pi over 2 to pi over 2, we're saying, oh yeah, this area here that's counting as negative is going to essentially balance out this area over here, which is counting as positive. So that's also going to be 0 for the same sort of reasons. So where does this come into play? Well, it comes into play maybe on an exam where someone asks you to find the integral from -5 to 5 of x cubed times cosine of x over x to the 6th plus 1. And you ask yourself, how the hell do I integrate that? And you're like, well, I don't know how. And then you see, oh, wait, there's a clue. And the clue is that that's -5 and that's +5. If you see that those numbers are opposite, it's not guaranteed, but it's a good bet, especially if this looks terrible, that this is an odd function and your job is to just say it's equal to 0. But typically you have to give some justification, meaning you have to not just say the function's odd, you have to show the function's odd. How do you show function's odd? Right, exactly. So we have to show that f of -x, which in this case would be -x cubed times cosine of -x divided by -x to the 6th plus 1. We want that to end up equaling the negative of f of x. So I would say you do get to use the fact that the trig functions have whatever sign they have. So you get to know that cosine and secant are both even functions, and the other 4 trig functions, sine, tangent, cosecant, and cotangent, are all odd functions. So it's true that cosine of -x is equal to cosine of x, because cosine is even. Also think about the graph of cosine, right? Cosine of a negative number is the same as cosine. Oh my gosh, do you guys hear that terrible noise? There's like a high pitch, like, anyway, I'm hearing it. So anyway, cosine of a negative number is equal to cosine of the same positive number. So cosine of -x is equal to cosine of x. So here's what's going to happen. We're going to get -x cubed, right? Because negative times negative times negative is still negative. We're going to get positive cosine of x. -x to the 6 is going to end up being positive x to the 6 plus 1. And then if we factor out the negative sign from the top, we get negative x cubed cosine x over x to the 6 plus 1, which is indeed equal to negative f of x. So it checks out, the function's odd, so then we can say this whole integral is equal to 0 because f of x is odd. No, cosine is even. So let me write it down. What's that? This whole function is odd, but it definitely is definitely depending on the fact that cosine is an even function. So let me actually write that down real quick just so you all know. So cosine of x and its reciprocal secant of x are even functions, meaning that cosine of -x is equal to cosine of x and secant of -x is equal to secant of x. The other 4 trig functions are odd. The sine of x, tangent of x, cosecant of x, and cotangent of x are all odd, meaning that sine of -x is equal to negative sine of x. And tangent of -x is equal to negative tangent of x. And cosecant of -x is equal to negative cosecant of x. And cotangent of -x is equal to negative cotangent of x. You don't have to prove those, is what I'm trying to say. Like, you just get to say those are odd or even at your leisure. They're not, no, they're not that great to prove, actually. Proving sine and cosine require the use of the angle sum formulas. They're not terrible, but you have to know the formulas to make work. Okay. So Integrals of odd functions, super nice when the limits are the same, you get 0. There is also a thing for even functions, which is less useful, but still not unuseful. So here's what the even function thing says. Let me give you an example first. Here's an example of what I mean. So we're going to find the integral from -3 to 3 of 9 minus x squared. Actually, I'm just going to graph it. So if I graph this thing here, I've got a downward opening parabola. Vertex is 0, 9. Its intercepts are 3 and -3. So here's what I'm going to do. Instead of finding all of this area, I'm going to say, let's find just half the area. And since this function is symmetric about the y-axis, aka it's even, we can say, oh, this is just going to equal double the area from 0 to 3. It's not super duper useful, but I will say, I do think it's easier to do this, right? Plugging in -3 just gets messy. Whereas if I do it this way, I get 2 times, let's see, if I integrate, I get 9x minus x cubed over 3, evaluated from 0 to 3. If I plug in, I get 2 times 9 times 3 is 27, minus 3 cubed is 27 over 3. If I plug in 0, I do get 0. So I end up getting 2 times 27 minus 9, which is 36. I personally think this is better than doing this. Integrate, I don't have a 2 anymore, James. Just kidding. Integrating this and getting 9x minus x squared over 3, and then having to plug in both -3 and +3. I think that it's easy to make a mistake with the negatives there. So this is something you'll see textbooks do often in solutions. You'll be like, how did they jump from this integral to 2 times this other integral? It's because they're using the fact that the function was even. But it has to have been an even function, right? It doesn't work if it's something else. So we can do this because f of x equal to 9 minus x squared is even. Or in other words, f of -x, which equals 9 minus -x squared. Well, -x squared is just x squared. So that's 9 minus just x squared, which is your original function. So it needs to be even. The f of -x is equal to f of x. This is less often used, but still useful. Question?
36 is the area of only the shaded part.
No, 36 is the total area. So I would say this shaded part has an area of 18. And then we doubled it to get the other half here. So that's what you do. You're essentially cutting the whole thing in half and then multiplying it by 2 to get still the same total area. All right, let us switch gears a little bit and look at some of these interesting word problems here. Go ahead first.
How did it, like, you took out the negative? I think it's the previously.
Oh, sure, sorry.
Like on the bottom.
Uh-huh.
How did it become negative? Wouldn't that change in full everything?
No. So let me ask you an important question. So this, I thought that's where you were going, because this comes up a lot for people. So, good question. What happens when you have like the negative of a fraction? Sorry. The negative of x squared plus 5 over x cubed minus 1. Right, but it can't go to both.
Yeah.
Because if it went to both, you're multiplying the top and the bottom by -1, which is, if you're multiplying by -1 over -1, you're multiplying by 1. So this could either get you negative x squared minus 5 over x cubed minus 1, or x squared plus 5 over negative x cubed plus 1, but not the other thing. So that's why when you're factoring the negative, you're only trying to factor it out from either the top or from the bottom, but not both. Okay, good question. And then you said number 6. I think you're not the other person. Well, we'll see if we get there. Which one's 62 here? I don't know about 62. It looks kind of like a bit much. I was gonna look at something else for. Oh, there was one other thing someone asked about that I just want to point out. So this, I see this integral as one of the homework problems. Integral sine of 2x over sine of x. This problem's easy if you know what to do, which I know sounds like a stupid thing to say, but that's how a lot of this works, is it's easy once you've seen the thing to do, but until you've seen the trick or the method or the inspiration, like how would you get there? So what I should really point out is there's some trig identities you have to be aware of. So here are some trig identities you need to know. I'm not going to write them all down. I'm just going to write down the ones I think are worthwhile right at this moment. I would say this is always true. You should always know sine squared x plus cosine squared x equal to 1. That's a super important trig identity. And then I would say there's two other ones that may come up. I don't know. Yeah. So the two I'm thinking of right now are the double angle formulas. Sine of twice an angle is equal to 2 times sine of that angle times cosine of that angle. So now I can imagine you all can figure out how to do this problem by replacing sine of 2x with 2 sine x cosine x, canceling the signs and integrating the result. I'll tell you one more trig identity for now. Cosine of 2 times an angle is equal to cosine squared of that angle minus sine squared of that angle. So I'm just saying you can replace sine of 2x with the thing it's equal to. And then if I do that, what's going to happen? Right, we're going to get 2 sine of x cosine of x divided by sine of x. I think you can see where to go from there. Okay. Let's look at a problem similar to problem 50 here, because I feel like this one has something. And no, sorry, this is from homework number 4 from section 5.3. There's a couple problems people asked about, also that I thought were good to look at. So let's look at this one. I'm gonna make the numbers less terrible though, because so this is similar-ish to number 50. So here's what we have: a bacterial culture, colony, whatever, increases at a rate of, I'm going to make these numbers suck less, 4 times e to the 3t bacteria per hour. If the initial population is 60 bacteria, find the population um 5 hours later. It's number 50-ish. Okay. So here's the thing I want to focus on first. They told me that this bacterial colony is increasing at a rate of 4 e to the 3t bacteria per hour. So that means the rate of change of the number of bacteria is equal to that function. So let's give our thing a name. I'm going to call it B of t or N of t. Let's say N of t is cool. So we say that N of t is the number of bacteria at time t. But they didn't tell us that. They told us the rate of change, which is another name for the derivative, right? You hear rate of change, you think derivative. A rate of change, really, you should say, that's kind of the most general description of what a derivative is. It's a rate of change of something, or it's how one thing is changing as another thing is changing. Oftentimes, but not always, right? Slope is a derivative because it's how y is changing as x is changing. So we know that the rate of change of the number of bacteria, dn dt, or if you prefer n prime of t, is equal to 4 e to the 3t. So if you know the derivative of something and you want to find the actual function, what do? the antiderivative. So we're going to say that n of t is equal to the antiderivative of 4e to the 3t dt. If you really wanted to be like super extra about it, you could actually throw in some limits of integration here and make this like from 0 to t or something. I find that to be more trouble than it's worth. I'm just going to find the antiderivative, throw in a plus c, and then figure out what the c is based on the initial condition. So we're going to anti-differentiate this. Is now that's, yeah. So we could either do this by, no, we should do it the long way. Fine. So the way you should technically do this is with a u-substitution. Although this one's small enough that I think you can get it without doing it. So, but we'll do it the long way, we'll talk about the short way. And first of all, actually what I'm going to do first is I'm going to use my constant multiple rule and bring that 4 outside of the integral. But you did talk about u-subs at the end of class yesterday, so we should start talking about them. So a u-substitution is just a method for essentially trying to make an integral simpler. And it's more than just that. But here's what we're going to do. We're going to pick u, in this example, equal to the exponent of my e there. So we're going to let u equal 3 times t. And then the next step always is to find the derivative of u. So usually we skip this step. I usually don't write du dt equals 3. Although that's a good step to take if you forget what happens next. And then we usually isolate du. So usually people jump just to saying du is equal to 3 times dt. And then actually we often end up isolating dt. Although it depends on how you like this, and we'll talk more about this in a minute here. So I'm going to divide both sides by 3 and say 1/3 times du is equal to 3. Sorry, is equal to dt. Apologies, not 3. Sorry about that. Okay. I like to think of this as a translation problem. You are translating from the language of your initial variable, in this case t, completely to the language of u. You can't have some t's and some u's. It's either all t's or all u's. So rewriting this with just u's, always make sure that your differential dt turns into something with du before anything else. I'm going to say it again. Make sure your dt or dx or whatever your differential is to start with, your d whatever, make sure that that transforms into the d with the other variable before you do any of the rest of the integral. There are good reasons for this, which we don't have the example to explain yet. But trust me, there's good reasons, which we will explain eventually. So dt is equal to 1/3 du. And now I can deal with the rest. E to the 3t is e to the u. I know it didn't seem like a big deal here that I did that order, but it is a big deal. We want to do it that way always. And then you could pull out the 1/3, but you don't really need to. We can just say, great, the 4 times 1/3 is 4/3, and the antiderivative of e to the u is e to the u. Plus c. And then we are going to change back to the variable we started with, right? Because if we're doing an antiderivative, we should always end with the same variable we started with, if it's an indefinite integral. If it's definite, you don't have to, but we'll talk about that later. So here we're going to say that n of t is equal to 4/3 e to the 3t plus c. I will point out, and I think I've said this before, that notably here, if you took the derivative of e to the 3t, you would get e to the 3t multiplied by 3 because of the chain rule. And I'll say this so many times it'll make my head hurt. If your derivative would make you multiply by a constant, your antiderivative is going to make you divide by that same constant. And that's why we end up dividing by 3 here. Because if you were to differentiate this, you would multiply by 3, and then 3's would cancel out, and you get back where you started. Cool. All right, but now we want to answer the rest of this question. We were also told that the initial population is 60 bacteria. So we're going to say, great, we know that n of 0, which is going to be 4/3 times e to the 0 plus c, should equal 60. Which means my numbers are not going to be very nice here. Oh, well, sometimes that happens. So 4/3 times 1 plus c equals 60. So my constant term there is 60 minus 4/3, which is 180 minus 4 all over 3. So it's 176 gross. Okay. So now my function here is now the number of bacteria at time t is equal to 4e to the 3t plus 176 thirds. And then to finally answer the question, how many bacteria are there 5 hours later? We would then plug in t equal to 5 and get 4e to the 3 times 5 plus 176 thirds. And then if you wanted to actually have an idea of what that number was close to, you would plug it into a calculator, because I have no idea what that number is off the top of my, right? E to the 15th is really large. So it's something big. Questions about that? Time back up. Okay, I got some time. Okay. Let me think about what I got here. No, it's fine. Yeah, sure. Cool. Yeah, that's good. Okay, let's see. Do I really want to look at number 62 here? Maybe we'll see. Let's look at number 2. Yeah, 62. There's so many words. I know. Sure, yeah. So I try not to do necessarily exactly the homework problems that are due for you, because like it's I'm kind of not supposed to. So we will look at 62 and see what I say, and then we'll look at these other ones as well and see what we can see. So yeah, reading. So I'm gonna read through number 62 and kind of write down the pertinent pieces of information here. And that's a lot of words. Photosynthesis. Much of the Earth's photosynthesis occurs in the oceans. The rate, okay, I see an important word, the rate of primary production, as discussed in exercise 61, depends on light intensity, measured as the flux of photons. That is the number of photons per unit area per time. For monochromatic light, intensity decreases with water depth, according to Beer's law, which states that, okay, here we have an equation. We have the I of x is equal to e to the negative kx, where x is the water depth and I is the intensity. So let's see, does this even make sense before we keep going? So if x is bigger, right, if we're more deep, is this result going to be bigger or smaller? Smaller, right? Because if you have, assuming k is positive, right? If you have e to a negative big number, it gives a small result. Okay, so it seems sensible. It's good, but it's good to check to make sure that like the things you're saying make physical sense if you're talking about a physical thing. A simple model for the relationship between the rate of photosynthesis and light intensity is that, okay, that P of I is equal to A times I, which is A times e to the negative kx. They didn't write that last part. I'm just filling it in because we know what I is. Where A is a constant and P is measured as a mass of carbon fixed, right? Because that's what, right? So you might not know this, you probably know this. I'm not a biology person. I'm a math person, right? Like, sure, whatever. But right, in photosynthesis, the plants are like fixing carbon, whatever that means, right? It was broken, they fixed it. I know that's not really, I know that's really not what's happening. I was just making a bad joke. It's the mass of carbon fixed per the volume of water per unit time. Well, that seems funky. We don't need to write this down necessarily, but it's helping me figure out what's happening. So I'll point out there, as stated, a simple model for the relationship between the rate of photosynthesis and light. So P isn't just the amount of photosynthesis, it's the rate of photosynthesis. So, right, P is the rate of photosynthesis. Okay. So the first question is, what is the rate of photosynthesis as a function of water depth? And I think we already answered it. Except I should have written it as P of X instead of P of I. Right? But as far as we're concerned, P is the rate of photosynthesis. And it's equal to A times I, which is A times E to the negative K times whatever the depth is. So I think I don't see anything else to say about that. Sure. So question A was, what is the rate of photosynthesis as a function of depth? Which is just X. So, I mean, we've already done it, right? We've written the rate of photosynthesis, P, as a function of X. Cool. Okay, question B here looks a little trickier. What is the total? Okay, so when you see the word total, just think, oh, I'm probably adding up some stuff. Adding up some stuff. We're probably adding up like a bunch of rectangles. Oh, wait, when you add up a bunch of rectangles, what are we really doing? We're finding the area under the curve, or maybe the volume under a thing. We're integrating in some way, shape, or form, typically. So when you see the total, that should be a clue that we're probably gonna have to do some sort of integration. Okay, so what is the total rate of photosynthesis of a water column that is 1 unit in surface area and 4 units deep? Okay, so here's my column of water. That is 1 unit by 1 unit and 4 units deep. Okay. So, yeah, this is... So let's focus in on this slice of water. That is at a depth of X. I want to know, what do I want to know? I want to know the total rate of photosynthesis for that slice of water. Well, I think I know it. I think for this slice that the rate of photosynthesis for that slice is equal to, I think it's A times E to the negative KX. I think. Okay. Wait. Yeah, no. Divided by the volume. Yes. The units here are not nice. I think that's it. I don't want to write down units, so I really don't want to do. Yeah, I think, yeah.
Confused about the rate. Why for question 50 we found like the antiderivative of the function given, but for this one it's just
So that's an excellent question. And what I'll say is, here they aren't asking us to find they're not asking us to integrate the photosynthesis yet, because, so I'll point out, right, here, I feel like rate is not, so usually I would say you're totally right. Usually be like, oh, they told us the rate of this thing, and then we're gonna anti-differentiate this thing because we want to undo that to get the function. But here, the problem is that photosynthesis is something that, like, unlike a lot of things, it's not like a thing where you can snapshot and just be like, it's like, this is how much photosynthesis there is at this moment. The photosynthesis you're measuring at this moment is still measured as a rate of something happening. Right? It's not like you can kind of add up all the photosynthesis and be like, we photosynthesized this much. You probably have to actually talk about like how much carbon was fixed if you were actually integrating the rate here. And I know that question, it's also, I will kind of punt this one a little bit and be like, my understanding of biology is not excellent, so there's probably some other stuff going on there that I'm not 100% aware of, but I'm pretty sure it's because in this question here, they're not asking us for the total amount of photosynthesis, And I don't know if you can actually see these words here, but they're asking us for the total rate of photosynthesis. So they're asking us to add up all the rates of photosynthesis to get a new total rate of photosynthesis. Yeah, so.
The 4 and the 1.
Well, so they told us the column of water had a surface area of 1 unit or 1 square, right? It's a 1 by 1 square, and then it's 4 units deep. And what I think this is going to amount to is that we are going to need to essentially, if I want to find the total photosynthesis, we're going to add up all of the slices. So this very top slice is going to kind of have the most photosynthesis happening because it's the closest to the top, and X is the smallest value. Whereas the slice down here at the bottom here is going to have the least amount of photosynthesis happening because it's the deepest, right? It's going to have an X value close to 4, and A times E to the negative 4 times K is going to give us the smallest value out. But to add these all, I'm sorry, I've been missing one little thing here. I forgot. My slice here isn't just the amount of photosynthesis happening, it's the amount of photosynthesis multiplied by the volume of water, essentially. I'm kind of maybe making up a little bit, but it's going to work out fine. So just trust me for a second here. So the volume of this water is 1 times 1 times how deep it is. And that little bit of depth there is a very, very, very small change in X. I'm going to call it dx. Okay. So now what we're going to do is we're going to add up all these slices by integrating. And the slices go as low as X equals 4 to as high as X equals 0. So we're integrate from 0 to 4 of a e to the negative kx dx. And I'm pretty sure that's right, but I'm not 100% sure. I'll be perfectly honest. I don't actually know for certain if that is the right answer to this question. I'm gonna go think about it after class to feel like to kind of get a better idea of what's going on here. Yeah. I feel like maybe I'm not answering that right. I feel like I've read the question wrong. Let me read it again. So here's the way I read it first. I read it as what's the total amount of photosynthesis occurring for this entire column of water. But I don't think that's what the question says upon reading it again. So let me read it again very carefully and tell you what I mean. So I'll point out, as we saw with that earlier question, the very first question in class about like the derivative versus the integral, that question arose because there was a question in the book that said like, is this integral equal to this thing? And we were like, we don't know how to integrate this. And we're like, oh, the question says to check it by differentiating. So it's very important to make sure we read questions as carefully as we can, myself included. So if I read this again, here's what it says really. It says, what is the total rate of photosynthesis of a water column that is, no, I feel like I'm still saying the right thing here. It's just here. So if I read question C, I know. What is the total rate of photosynthesis of a water column that is 1 unit in surface area and X units deep? So I think for question C, I think it's the same idea, except now you're going to go from, instead of from 0 to 4, you're going to go from 0 to where? Right. So then I'm going to write a e to the negative k t dt. Nobody hates you. Well, that might not be true, but I mean, the Dell doesn't hate you for sure. He's not assigning these homework problems because he doesn't like you. He's assigning these problems because he thinks they're important. And then the last question is, what is the rate of change of that? Okay, what's the rate of change of this integral? What's the derivative of the integral of a function? So close. Kx. The derivative of the integral from a constant to x of a function is the same function, but you get x instead of t. So I think this example, although it's very confusing, to be honest, is partially just to get at your understanding of the fundamental of calculus. Welcome to math. Math is reading things carefully, right? A lot, especially in the 17 series, a lot of the questions are these applied biology questions where you actually have to read the thing to understand what the question is asking. So yes, your ability to read and understand words that are mathematical or not is very important to your success in this class and 17C. And if you ever take stats, also that. Sure. Let's look at, sorry. I actually spent a little bit of time talking about u-substitution because that is where things are going in the future. So let's talk about u-sub for a good 11 minutes here. So here's the whole idea with the u-substitution. You have something that's too complicated, like the integral of, say, I don't know, x squared times x cubed plus 1 to the, let's make that a 3x squared, and let's say we have a square here. Okay, I'm going to point out, this one we could multiply out. In fact, we are going to multiply it out. So if I multiply this out, let's see what I get. I get the integral of 3x squared times x cubed plus 1 squared is x to the 6th plus 2x cubed plus 1. Distribute. You get 3x to the 8th plus, sorry, the integral of 3x to the 8th plus 6x to the 5th plus 3x squared. And yes, I could have factored out a 3, but I put the 3 in there to make the numbers a little nicer. Then we get 3x to the 9th over 9 plus x to the 6th plus x cubed. And now I'm going to do something. Oh, plus c, sure, plus c. But anyway, so I'm going to factor here. So I want you to see what this is actually equal to. So I'm going to point out, well, actually, we'll come back. So, will we come back to that? Sorry, I keep going back and forth. No, let's see. So I'm going to factor out a 1/3 and write this as 1/3 times x to the 9th plus 3x to the 6th plus 3x cubed plus c. Sorry, I do this line here like I was going to do something beneath it, and then I decided to do more here. And actually, I'm going to factor out as well an x to the, I feel like I'm making an error here. I am making an error here. Small error, but it is an error. No, am I? Sorry, I keep looking at this like I'm making a mistake, and now I'm not sure. No, that seems fine. Seems fine. Sorry, I have to actually think about this for a second. I see the issue here. I don't love this example I picked. Oh well, so let's go the other way and talk about it. So the other way to do this is by making what's called a u-substitution. So here's what you're really doing. You're really trying to undo the chain rule. You're trying to think of this is the derivative of some function of a function, and you're trying to guess what the inside function piece was. And it's usually the inside of some thing that's written there. So in this case, it's a pretty good bet that my inside piece is x cubed plus 1. So we're going to say that u is equal to x cubed plus 1. And then we're going to find the derivative. Our du dx is equal to 3x squared. So our du is equal to 3x squared times dx, which we happen to have perfectly, which is great. So I'm going to rewrite this just slightly so that things are in order. You don't need to do this at all. I just like to because I find it convenient. So I'll point out that 3x squared times dx is exactly my du. Again, making sure I take care of the dx du changeover first, and everything else second. Oh, my x cubed plus 1, that's u. So what I really got here is the integral of u squared times du. Yes. Doesn't have to, but yes. Well, but it can't. Like you can go either way. So yes. So we're gonna get u cubed over 3 plus c. Okay, here's what I want to point out. This is I'm gonna call this just for a second g of x, just to make it more obvious what's happening here. If you took the derivative of some function cubed, you would get 3 times that function squared times the derivative of that function. Oh, right. You would get 3 times your function squared times the derivative of that function, which is exactly what's happening here. So this is going to look like, now I'm going to plug back in, x cubed plus 1 cubed divided by 3 plus c. Now the question that might be weighing on your mind is, are these the same? And the answer is, they're the same enough. Let's multiply it out and see. You multiply x cubed plus 1 cubed, you get x cubed cubed plus 3x cubed squared plus 3x cubed to the first plus 1 cubed, all divided by 3 plus c. Let's see, is that the same? Right. I would say they differ by a constant, but that's fine if they differ by a constant. Or yes, you could say this constant here and this constant here, really just sucking up that 1/3 to make them the same. So yes, they are the same enough. They differ by at most a constant, which means for all intents and purposes, we're good to go. So with u-substitution, you're looking for a good candidate for u. And ideally, you would love to make a choice for u so that the derivative of u is also in your integral. And it was here, right? We picked u equal to x cubed plus 1 for 2 good reasons. The first reason being, the best reason being its derivative was also there. And the second best reason being it was stuck inside some other function, being squared. Yeah, we have time. Okay, so what if, oh my gosh, what if we could turn the page here? What if we want to say find the integral of, sure, x squared times x squared, not my favorite choice here, James. Fine. Cosine of x cubed. Well, same idea. I still have the same things happening here. I have x cubed being stuck inside a function, and its derivative. Well, let me ask you: is its derivative there?
Yeah.
Right, without a 3. But is the 3 something we can account for? For sure. So we ignore any differences of by a constant multiple because we can always fix that. So here we would let u equal the inside of the cosine function. My du dx is equal to 3x squared. Now people do this slightly differently depending on what they prefer. My preference is to make this equation look like the right side looks like something in by integral. So I would say that du equals 3x squared dx. I don't have a 3, so I'm going to divide both sides by 3 and say that 1/3 du is equal to x squared times dx. There are other ways of doing this, but I'm pretty sure this is how Dedel does it as well. So I would stick with doing it this way. I can talk about other ways later. So I'm going to take my x squared times dx and replace that x squared times dx with my 1/3 times du. And then I deal with the rest. My cosine of x cubed, that's going to be cosine of u. Now we integrate. The 1/3 multiple just hangs out. The antiderivative of cosine of u is sine of u. Slap on a plus c. Since it's an indefinite integral, we need to end with the same variable we started with. So it's got to be 1/3, excuse me, sine of x cubed plus c. If you took the derivative of this, you do the chain rule, you'd exactly get that. Now, what if we have a we got enough time. What if we have a definite integral? Like the integral from, sure. Sorry, 1 second here. 0 to 2 of, I don't love rough, the same choice I'm making here, but fine. Of x squared times the square root. Sorry, this is just a standard example and it happens to have the same sort of substitution. Sorry, they've all been x cubes. So let's say that's our integral. Yeah, it's gonna work out fine. Yes, okay. So we're gonna do a u sub here, and you have kind of a choice here. I'm gonna tell you what I recommend. So we're gonna make the same u substitution we made before. U is equal to x cubed plus 1. Here we get du equal to 3x squared dx once again. We have 1/3 du equal to x squared dx. So replacing things, my x squared dx, that's going to give me my 1/3 du. And my x cubed plus 1 is going to be u. So I'm going to rewrite this as the integral of the square root of u du. Now, what about the limits of integration? Well, you have choices. My personal opinion is the best choice is to change them. Question? Oh, what about the 1/3? I forgot it completely. Thank you. Yes. I even wrote it right there. I shouldn't have forgotten it. Okay. So my opinion is we should change the limits of integration. So we were told that the limits were x equals 0 and x equals 2. But if x equals 0, then u is going to equal 0 cubed plus 1, which is 1. And if x equals 2, u is going to equal 2 cubed plus 1, which is 9. And now we integrate. This is u to the 1/2. The antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2 or multiplied by 2/3. We don't need a plus here because it's a definite integral. So we're just going from 1 to 9. And we don't change back. We changed everything to be in terms of u, so we're in terms of u. So we've got 2/9 times 9 to the 3/2 minus 1 to the 3/2, which is 2/9 times 9 to the 3/2 is the square root of 9 cubed, which is 3 cubed, which is 27 minus 1. That's 26 times 2, that's 52/9. That's how, oh, sorry. That's how I would prefer to do it, how I prefer that you do it. However, some people don't like to do that. Another way to go here, which you can also do, is you can not write the limits of integration. You can say it's going to be 1/3 the integral square root of u. I really think you shouldn't not write them. I think you should, if you're not going to change them, you should be like, well, you can't just write 0 and 2 because that's wrong, but you can write it's from x equals 0 to x equals 2, which is kind of funky, but it's not wrong. We anti-differentiate. We get, again, our 2/9 u to the 3/2 from x equals 0 to x equals 2. And then we change back to our variable x. So we rewrite this as 2/9 times x cubed plus 1 to the 3/2 from x equals 0 to x equals 2. And now we can plug in our values and get 2/9 times 2 cubed plus 1 to the 3/2 minus 0 cubed plus 1 to the 3/2. And oh, look, it's the same. 2 cubed plus 1 is 9. So now I get 9 to the 3/2 there, and then 0 cubed plus 1 is 1. Oh yeah, 1 to the 3/2 there and there. So either way you do it, you're going to get to the same answer. I just think this requires more writing and kind of stuff, whereas doing it this way, you don't. So I would always recommend changing the limits of integration to being whatever the u values are.
So to change, you have to plug in the values of x and
Into your u substitution choice, yeah. So whatever you pick u equal to, you just plug in the x value, the x limits of integration values to find the corresponding u limit. Now be careful here. Sometimes your u values will feel like they're out of order. Like you'll have like x from 0 to 3, and you'll get a corresponding values of like u from 5 to 2. You don't flip the order to make it the right order. You just leave it in the out of order. If you do want to flip it, you can, but you have to then change the sign out front. So don't just change the order because it feels right, change the order because you have changed the sign. Yeah, it does happen more often than you would think, that when you do the U sub and you change the limits of integration, they do end up being out of. All right, that's all for this week. We'll see you all next week, where we'll be talking more about U substitution and maybe integration by parts.